Hi everyone. Today, Fed, Rafael, and I will take you on a walk through TigerBeetle's LSM-Forest. I'm Chaitanya, and I'm interning at TigerBeetle over the summer. So before we jump in, let's take a step back and try to understand why TigerBeetle needs a storage needs an LSM tree, and more importantly, what is an LSM tree. I think Joran did cover some of it, but I'm going to touch on those points again. Some of those points, yeah. So, like Joran said, we have a write-ahead log. When the consensus protocol commits stuff in the write-ahead log, it then has to be applied to the in-memory state on each replica. Now, this in-memory state must be checkpointed to disk because the log is finite and needs to wrap around. Again, this checkpointing must be incremental because you can't checkpoint GBs of data to the disk. It would be prohibitive for performance. And also, we must do so without incurring random I/O.
Can you move a little bit?
Yeah.
Yeah.
So enter log structured merge trees. They satisfy all these nice properties. So log structured merge trees are ingestion optimized data structures that form the storage engine of many modern databases. Some examples are RocksDB, LevelDB, some popular implementations of LSM trees. So this is what an LSM tree typically looks like. Again, repeating what Joran said, we have a write-ahead log. Now we apply the changes to the into an in-memory buffer. When the in-memory buffer reaches capacity, we flush it to disk as a sorted table. Now the LSM tree on disk, it logically consists of levels, and each level has exponentially increasing capacity. Also, periodically, when levels exceed their capacity, the LSM tree must compact things across levels, compact sorted tables across levels, and move them to lower levels of the LSM tree which have more capacity. So this is how the write path looks like in an LSM tree. For a read path, you can it's quite intuitive. You go first to the in-memory buffer and see if you can find a key there. Otherwise, you have to go through all of the levels of the LSM tree to find the first occurrence of the key. So that is a brief overview of what an LSM tree is. At TigerBeetle, we built our LSM tree from scratch. And the reason for that, again, building on what Joran says, is we adhere to a set of principles we call Tiger style, which is safety, performance, and developer experience. More specifically, we use static allocation in Zig, limits on everything, and tried to exploit determinism wherever we could. So, Rafael, can you tell us a little bit more about how static allocation helps us?
Of course. So, yeah. Memory allocation, it looks like a simple operation. You just need to find a spot in memory and care to release it after use. So, but that's not that simple. There is an entire industry around that problem. So things like static analysis tools, garbage collectors, and even a programming language trying to solve that. And even if you could do memory allocation right, that's still not deterministic. It still can fail, and most software can't recover from allocation failures. And we can agree that not having to deal with memory allocation is a good thing. But how is that possible, not dealing with memory allocation? That's a question asked so often that our colleague Phil wrote an excellent blog post explaining that. I'm not going to answer how is that possible. You can read the blog, but I'm going to answer what are the benefits of doing so. So by doing memory allocation statically, we have to put limits on everything. Things like the maximum number of clients, the size of a message, the number of replicas, and everything has limits. For example, our LSM implementation can handle 100 terabytes of data using only 1 gig of RAM for memory manifest. Because we know the size of manifest, we can allocate enough memory for doing that. And from limits, we can benefit from extremely predictable performance and resource efficiency. So we have user land page cache called the grid. And the grid is responsible for caching blocks that we read from disk and evicting old blocks that are not more necessary. So we can tune that grid to hold the bare minimum blocks that we can reference at the same time, or we can put all of the blocks on memory. So the cluster operator can just provide enough resource to run a TigerBeetle instance that will not experience out-of-memory failures, even running in a micro VM or in a powerful machine. And single-thread data plane. That's another principle that we follow for a good reason. So with single-thread data plane, we have each request handled in a single thread, one by one, in a serial and ordered way. So by doing that, we can skip costs doing locks and synchronization between threads. And it can be counterintuitive, but it's in fact very efficient, because you can still do multiple I/O in parallel using Linux I/O URI. And for doing that, we have strict serializability and isolation for free, because you don't have concurrency clients putting data at the same time. But the most visible effect the end user can experience is a predictable tail latency, because the client has no surprise with another client running expensive workloads or doing lock contention or deadlock by repeating the same data. That's a good thing. So Fed can tell us more about how the single thread design can influence the compaction pacing. Over to you.
Cool, thanks Rafael. So compaction in TigerBeetle on LSM trees is quite a topic. But mainly our compaction focuses around three things. It needs to be incremental, it needs to be pace, and it needs to be deterministic. Now, when I started at TigerBeetle, my background was not in the database scene. I came from, building web apps with Python, all that fun stuff. When I think of compaction, I think of like something that's background work, something that's asynchronous, kind of runs at its own speed. That's not at all what compaction is in TigerBeetle. Compaction in TigerBeetle is, like everything else, deterministic, and it's driven by consensus. This gives us a few really useful properties, but it can also be a bit interesting to wrap your head around at first. I'll touch on that a bit later, but let's get back to those first 3 points. So compaction needs to be incremental. The reason is write stalls. So you can't have it where even with our compaction being paced and being deterministic, if we try and do too much work in one go, the client will see a latency spike. As a result, we need to do things incrementally. To do this, what happens is, Joran mentioned batching earlier. We rely heavily on batching, and when we receive a batch of transfers, we sort those 8,000 odd transfers in memory and keep around a partially sorted batch of buffers that we then only need to k-way merge on in the final step, rather than having to sort a large buffer that could be 256 megs. It's paced, so we only do the work that's required and we don't run ahead with work. So when a batch comes in, we essentially sort and process the previous, not quite the previous batch, sorry, skipping over a bit of terminology, but we use something called a bar, which is a group of batches that we group together for compaction and for other things. We do the amount of work required to run compaction for the previous bar. So just enough that's required, no more, no less. And then lastly, the big one, determinism. We can sort of look at compaction as a process that takes in an existing state and outputs a new state. And with all of the other principles of TigerStyle and in TigerBeetle, this means that all replicas will converge on the exact same on-disk structure. This is not it's not a background process that is, merging things together at its own pace. So how does performance look with all of this? Because if we're running these requests, then we're blocking client requests based on what other databases would consider to be a background processing job. So the two sort of things that we do about this, the one is pipelining, and the other one is exploiting queue depth on modern NVMe drives. The performance of NVMe drives is through the roof. You can get now on the consumer market drives that can do 10 gigabytes a second of write speed. The problem is not the write speed. The problem is actually giving these drives enough queue depth and enough work that they can hit those numbers. So this diagram, I'm not going to go into detail, don't worry about it. But essentially the key is we have three sort of resources. We have memory, CPU, and I/O. Memory we use as a sort of forcing function for our concurrency. We can say, we bound our compaction to run with X amount of memory, so that can place a limit on how much concurrency actually goes on. And then we have CPU work and we have I/O work, and a sort of standard thing that we don't want the CPU to be waiting idle while we're writing things to disk. If we can queue off a bunch of writes while the CPU does its work, that's great. I'm going to hand over back to Chaitanya now, just to take us through some deterministic storage and workload awareness.
So we've been talking about determinism and how it's one of the primary reasons why TigerBeetle wrote its own LSM tree implementation. So what are the benefits that come out of deterministic storage? So we get byte by byte verification of data files across replicas, and this is great for operator experience. And this is something that some of the other popular LSM trees don't offer out of the box. Then we get optimized distributed recovery. So if a block on one of the replicas is corrupted, you can simply fetch it from another replica, and this comes out of the symmetric nature of the data files on each replica. So that is another good thing that comes out of deterministic storage. And then finally, this ties in with the Whopper that Joran talked about. We get much better test velocity because now with deterministic storage, we can reproduce a bug over and over and over with just a single seed. Yeah, that's what we get out of deterministic storage. So I'll talk a little bit about workload awareness now. We realize that most of the workload in TigerBeetle is immutable, and the way that we exploit this immutability is by storing disjoint data sets in disjoint LSM trees. So we started from an LSM tree, so we have now we have a bunch of LSM trees because we store disjoint data sets in disjoint LSM trees. The way that we are able to do that is using Zig's comp time to avoid length prefixes. That makes the memory overhead of maintaining so many LSM trees on each replica cheaper. So this, of course, is good for both read and write throughput. So for write throughput, since data is immutable, you don't need to compact it. So that's what we get from write throughput. And for read throughput, if you want to say get transfers or accounts, you go straight to the tree with transfers and accounts. You don't need to page in any other data. And what we also get out of this is better spatial locality and cache efficiency. So again, you only page in the data that you want. You don't need to get in irrelevant data. So another thing that we exploit from the workload is monotonicity. So we maintain key ranges for the entire LSM tree and for all of the on-disk levels. What we get out of this is our negative and positive lookup performance both benefit from this kind of this optimization. So if we realize that our workload is monotonic, we can validate that a key does not exist within our LSM tree simply by looking at these key ranges. So we don't need to go through the exercise of going through all of the LSM tree levels. And also, this also benefits positive lookup. So we know that a key exists. we can skip looking through certain levels if it doesn't exist within the key range of those levels. So yeah, this is about workload awareness. I'll hand it over to Rafael for queries.
Well, how can I speak about queries here at DuckDB Labs? Well, but I think that we can all agree that queries is the main function, main reason of database to exist. But in TigerBeetle, we need to be predictable. So to be predictable, we need to do just enough work to complete a request. And this idea plays an important role in data ingestion, but we can apply the same thing for queries in TigerBeetle. So we can only accept queries that we can measure that amount of work to complete. So we don't want any runway queries running on or single thread data plane. And speaking of single thread data plane, by executing each operation serially, we can assign a unique and monotonic increase identifier to each operation that we call that timestamp. And our query exploit that ability of having a timestamp because we can take advantage of timestamp to return data that is already sorted, not have to do any extra work in auxiliary buffers. And we can talk about buffer without touching limits and static memory allocation again. So we don't allow queries that can return unbounded amount of data because that would exceed our pre-allocated buffer. So as you just saw, we have LSM-Forest because we have our LSM-3 and each index is an LSM-3 by itself. So scanning an index in TigerBeetle is just a sequence of lookups by key because you can use the prefix as key, so one index is just a simple lookup. And by doing multiple lookups, we can take advantage of having a fixed buffer because that's essentially the same disk block that we fetch from disk, so we are limited to the disk block. And we can combine multiple scans of that using algorithm like zigzag merge that can materialize data without having to fetch ahead. So that's a simplification of what zigzag merge would do with multiple index. So all of that index, the main idea is to have all index acting like streams of data that can be fetched always from the same buffer. So of course, with that in mind, we can't accept to have limits on our queries, but the efficient way the end user can see is that every query, being that a complex query or simple query, is always limited to the maximum message size, so there is no spikes executing any kind of query. And of course, we can export data to a specialized OLAP database like DuckDB for more sophisticated queries. And that's the main idea behind our actual implementation of queries. So I'll hand it over to Fed to finish with the conclusion.
Thanks. So unfortunately, we don't have a cool demo like you're under.
Yeah.
You can share at the cool logo on the screen. Yeah. So to sort of wrap it all together, it was a bit more of a run than a walk through the forest, but really, what we try to do is take the principles of TigerStyle, things like determinism, and realize those to actually sort of solve the problems that need to be solved. And a lot of that flows through that sort of being the work on compaction and, you know, not running things as a background job. I mean, it's super tempting, right? If you think, hey, like I'm idling right now, why shouldn't I just run ahead with work? Why should I wait for the next thing? Things like queries that are, you know, almost by design dealing with unknown amounts of data. How do you make that respond in a fixed amount of time, fixed buffer sizes, all of that. Things like static memory allocation, something that I definitely took a bit of time to get up to speed with the first time I was doing. I mean, it's something you take for granted when you're using a higher level language that you just sort of allocate. You don't even think about it. So it's not a conscious thought, right? Like we all know languages that panic on allocation failure. And really, all of these concepts might add a bit of slowdown initially when you get started and when you're sort of working on things. But they really enable such cool things like our deterministic simulation testing, the VOPA that Joran mentioned. They allow you to sleep soundly at night. And when you're dealing with a sort of storage engine that's hopefully going to be storing, critical financial transactions for entities, who knows how large you're dealing with, however many hundreds of thousands a second, that's sort of what you want. So, thank you.